So we'll continue with TCP today. Your first assignment is due on Wednesday, that is 2 days from now at 9 p.m. This would be on grade scope. I think some of you already started submitting, so you should have some sense for how it works. Hopefully there won't be any hitch, but I would suggest that submit something before, so to make sure this all works smoothly. Then I already mentioned this for your quizzes, your in-class quizzes with 5% of the total grade. I'll have a bunch of them over this semester, and I'll take the top, I think 75%, so you can miss a few, that's okay, but okay. Your exam is next, not this Wednesday, but the following Wednesday. It's due in class. It's October 1st. The exam will only have topics, the application topics, including what we did for the application layer. Nothing from transport layer will be included. We're going to split this class into 2 rooms because this is hard to write an exam with all of you with 180 students. So the other room would be new computer science 120. I don't know if you all know where that is. It's just first floor of the computer science. I will let you know at some point which students will be taking the exam in which of these rooms, and basically just have a cutoff with alphabetically. I'll just go and have a cutoff. And we have TAs as well as we will be there in both of these rooms, so hopefully it will be. And if you have accommodation to write your exams in SASE, you should, I think I got some emails already, but please let them know. Okay, any questions about anything so far? Yes.
Just to confirm, my office hours on Zoom still now?
Yeah, why not? Yeah, unless I say anything, it's the office hours.
Okay.
Yes. I can give you like a sample maybe, but essentially I'll talk a little bit more about the exam as we get closer to it, maybe next Monday. I'll give you some more logistics about how the exam. Oh, one thing I should mention, maybe this will be useful to know. I should also put this on the form. Is that I allow, it's a closed book, closed note, but you can get one sheet of paper in which you handwrite any notes you want. It can be on both sides. It has to be handwritten. It cannot be generated. Yeah, like a A4 sheet. Yeah. I haven't planned on that yet. No, maybe next time when I do this, I will do something. Alright, so let's continue with where we left off with TCP. So remember we're discussing how transport layer works, and then we sort of moved into one specific transport layer protocol called TCP. And this is the most popular transport layer protocol. Large fraction, up to 80% of the internet used to use TCP as of a few years ago. Now that has gone down a little bit because of this new protocol called HTTP, which we'll discuss later. But yeah, so that's why we're going to discuss TCP. First of all, transport layer. What are the 2 main abstractions the transport layer provides? Yeah.
End-to-end connection?
That's one. There's end-to-end abstraction. Right? It's not an end-to-end connection so much as an end-to-end abstraction. So you're creating an end-to-end connection to create this abstraction. Can somebody tell me what that means? What's an end-to-end abstraction mean? Yes?
It makes it seem like there's a direct pipe between the sender and the receiver.
Yes, it makes it look like there's a direct pipe between the sender and the receiver, even though underneath it there isn't. You're actually going through the internet over many hops, but it gives you that illusion for the application layer. Right? Okay, what is the other abstraction? Demultiplexing, what does that mean?
It uses like the IP.
Right. So because the transport layer connection can be used for many different applications, all of them are sent through the same pipe, right? There at the end of the day, they're just packets that are being sent. So we have to, so there are multiplex. This is the word we use. Multiplex means using the same resources to provide service to many different applications. It's usually called multiplexing. But then if you have to do multiplexing, you need to do demultiplexing, because if you actually then put all everything using the control flows, then one of them you have to figure out how to which application this packet has to go to, so that you have used some kind of an identifier. This identifier is called what in TCP? What identifier do you use to demultiplex? A port number is what you use to demultiplex. So a port number is just any number. I think the last number is 80,000 or something. I forgot what it is. But yeah, so you have this number that tells you which application you have to do. And so this means that if you now have to create an end-to-end connection, irrespective of what transport layer protocol you're using, it has to provide this kind of port number, because that's not specific to one transport layer. The entire transport layer has to provide, any transport layer protocol you write has to provide this. That's how it's called. Okay, so that's and then what are the two main kinds of transport layer protocols we discussed? There are two, which is very popular. One is called TCP, the other one is called UDP. You don't need to know what they stand for. TCP is the most popular one. It is connection-based. Sometimes you call it stream-based, and it provides reliability and in-order delivery. Because at the transport layer, packets cannot be sent in one chunk. It has to be there's a maximum segment size called MSS, sometimes called maximum transport unit MTU. These all mean the same thing. Essentially what it means is that I cannot have a packet that's larger than a certain size. I cannot send it. Which means that if there is a packet, you break it down and send it. It's stream-based means that when I break this down and send it, even though the packet may take different routes, they're going to come there in order, they're going to be delivered in order, and that's why it's called stream-based. So it's sort of like almost like I'm actually sending a stream of data, even though I'm not actually sending a stream.
So the CPU provides some type of instruction, but it really uses
No, it actually provides the instruction. It actually creates it. And we see how it creates it. Alright. So that's where we are. So we started discussing TCP, but one of the things that TCP does is that apart from being stream-based and reliable and providing in-order delivery, the other thing it does is it's connection-based. Okay? What does that mean? It means that before starting sending any information, I need to exchange some information between the sender and receiver. Usually this is to exchange state information or any other signaling. This is called signaling. So you start exchanging enough information so you can start. And so that is done, and that is what we discussed when we discussed the application layer with HTTP. We said, oh, I have to first create a connection, and that's after that, only after that can I actually start sending HTTP requests. That creating a connection is basically what we're doing with this handshake. Right? This is what that means. And so that is done using what is known as a three-way handshake. So I have a client and a server. It could be two hosts, it could be anything. And so what I first have to do is I want to send the information. I have to do this. First from here, let's discuss it. Initially, even before I create this packet, what does the client need to do to create this? Need to know to create this data. The first thing I need to do.
The port and IP address of the server?
Yes, the port and the IP address, the destination in this case is the server. Because if I have to connect to any network on the internet, I need to know that IP address. But if I now want to also create this TCP connection, I have to know that port, because remember that the endpoints are identified by the source port, source address, the IP address, destination port. That's the definition of a connection. And so I need to know this information. I already know my own information, my source port, because I have a port in which I'm binding. This is usually called an ephemeral port because it can be anything. And then I have my source IP address. So that's the information I need. Okay, so that I have that information. I can start creating the packet. And then I send this first packet to my server. What's this first packet called? Somebody else. What's SYN packet will have a bunch of information, including the source port and the destination port. But the most important information that we have here is the sequence number. So the sequence number, I'm going to call it X, can be some number that's the starting sequence number. So this means that once I establish this connection, all packets, subsequent packets will start from that sequence. So if I have sequence number 1, it will go from 1 and so on. If the sequence number is 183, then we go from 183. So whatever number, right? So let's call the sequence number is some 100. And then there is an acknowledgement. Okay. What will the value of this acknowledgement be? Anything, because it doesn't matter, there is nothing to acknowledge, it's my very first packet I'm sending, so it can be anything. So it can be any. So, and then I send this, when I send the SYN, the response would be something called a SYN act. The reason it's called a SYN act is because it's an act for that SYN, and it's a new SYN in itself, because TCP is bidirectional, which means I need to create connections in both directions. And so the way to create a connection is to actually send a SYN and then get back an ACK, which means the other side, the server, also needs to send a SYN and get back. Right? And so, but instead of doing it 2 times, so sending an ACK and then sending another SYN packet, you actually combine that into one. That's called a SYN ACK. And so that would have, this would have a new sequence number. So the sequence number would be something like Y. It can be some another completely different number, 380. And then we have an act, but this act will say 101 because this act is basically saying, oh, I received this SYN, that's an act for the SYN. But the way TCP works is that instead of acting the packet you receive, you're going to act the packet that you're expecting next. Right? So instead of saying, hey, I received 100, you say, hey, I'm expecting 101. Alright? Here again, there's a slight subtlety here. It's not packet, it's actually the next byte you're expecting. But let's not go there for now. Let's just look at packet. Assume that packet is easier for me to explain. When you do your assignment too, this will be very clear to you, so I'm going to leave it up to you to figure this out. Once I receive this, I then send back an ACK for that SYN. This would say my X would be, what would be X? Is a sequence number for this last ACK on the 3-way handshake. 101. This is the next packet. This was 100, so this is 101, and my ACK will be what? Yeah.
381.
381. The caveat here is that this is actually doesn't. It's not really 381. The number of bytes, 380 plus the number of bytes, and expecting that. So this is how your three-way handshake works. So now, of course, at this point, my connection, the one-side connection has been established. At this point, the connection on the other side has been established, right? And so, which is why when we discuss HTTP, we said I have a 3-way handshake, but then, actually, how many RPGs will this take for client to establish its connection? One RTT, send a request, I get back a response. But how many RTTs does it take? So, okay. So, at this point, my connection is established. Even though the other side hasn't established its own connection, that's okay. I don't care about that. Which is why, when I send an ACK, I can immediately also send my GET request when I'm doing HTTP because the connection has been established to the other side. Which is why we didn't take that into account. If you remember, we drew this, we said 3-way handshake, and then we had another line. It said that's the get because I don't have to do that. That's it. Which get? This get? That's okay. I'll wait for the acknowledgement to actually create the connection and then I will just store it. Obviously, that's a good question. I can't send anything back because that has not been created yet. So that's it. Now, what happens when this tear downs? Exactly the same thing has to, every time I create this connection, I use it to send my data, I need to tear this down. And just like you have to tear down, just like this is a three-way handshake because I want to create the connection in both directions. When I'm tearing down connections, I need to also tear them down on both directions. Alright, I need to tear down this from the client to server connection and the server to client connection. So the way you do this is to send a FIN packet. So I send a FIN, and you send an ACK back saying, okay, that side of the connection is done. And then on the other side, the server would then send their own FIN and get an ACK back. Only at this point is this TCP supposed to be closed. So I send a FIN, I get an ACK back. I'm still in a wait state. I won't close my connection because I could still be getting data from the other side. That side has not closed their connection yet.
What is that?
It's just like a SIM. Just like saying, okay, this is a FIN packet. FIN simply means, oh, it's a special packet that says this means I'm SIM. Okay, and I send this response, but at this point, for example, if I'm here, right, I can still, the web browser can still send me more data because that side of the connection has not closed yet. So I have to still wait a little bit. Only when it's completely closed is this whole TCP supposed to be closed. Now, everything I've said so far is all very nice because I haven't discussed what will happen if one of these packets get lost, maybe an ACK gets lost in the middle, or maybe this can be worse, actually one of these SIMs get lost, and then what, you keep waiting because you don't know whether it's going to close or not, and so there's lots of complications that can happen. I'm not going to discuss these actually. We'll discuss something in a slightly different context and maybe we'll get here, but I'm not going to discuss these. But here is basically the state transition just for the three-way handshake and the closing. And I don't know how many of you have you all learned state transition diagrams? Like state machines? How many of you have never heard of state machine? Okay. What context have you learned state machine in? The rest of you who have. Okay, yes. Yeah, if you've done theory of computations, now you use state machine. I think there's some kind of software engineering class when you use state machine. So you don't need to know this. I'm not going to ask you any questions here because this class is not about state machines. But the state machine essentially means that you can be in a different states, right? You can say, okay, I'm about to start. I've created my connection. I can send data. I've been closing. I'm somewhere in the middle, and you represent this. You can actually represent this entire protocol of just the connection establishment and the connection closing using this kind of state machine. And you say, okay, if I receive a SIM, then I go from this state to this other state, and so on. But the thing is that the reason I'm showing you this is that this is actually just that part alone is this complex. The entire TCP-based state machine is actually really, really complex. There's been a lot of work on trying to build this and trying to reason with it, but yeah, it's pretty complex. And the reason for it is that you have to take into account every corner case. So what happens if the second ACK gets lost? What happens if something else happens? Alright, so that is how the TCP connection establishment works. So now let's look at how TCP will actually work. Now that I've established a connection, I'm actually going to start sending data, and essentially I'm sending a GET request, for example. So how will I do inorderability and reliability, which is two of the things that I want to do, two of the properties that the TCP has. Now, TCP is also connection oriented. We already discussed how that works. So basically, doing this three-way handshake. It's stream based. Stream based is sort of similar to inorderability and reliability. So if you have these two, you basically get stream based, which is why we don't mention this. So let's talk about how you will do inorderability. First of all, what is inorderability? Yeah. Packets arrive in order. Okay. Why will packets not arrive? Yeah.
They'll take different routes.
Because they take different routes, right? And so let's look at the scenario that we are considering here. So again, I have a client and a server. I've already created this connection. Now, you could think of HTTP is now sending the GET request. So what happens when HTTP sends its GET request? The application sends a packet. From TCP's point of view, it doesn't care whether it's a GET packet, GET or what, or maybe I'm just sending a good protocol. It doesn't matter to me. It's a packet from the application. I have to send it out. That's all I care. Okay? So this means that this is exactly what is happening when HTTP sends a GET request. It gets to the TCP layer. TCP layer completely forgets the fact that it's a GET request and no information about semantics. It doesn't care. However, this packet could be large. GET is usually not large, but let's assume that this is a big large packet. So what I will do is to separate them out. And I'll break them into pieces and assume that the sequence number for this one was 1, the sequence number for this the next string was 2. Then I have sequence number 3, 4, and 5. Right, so these are the three sequence numbers. I have to send these to the client, to the server. And so I'm sending 3, 4, and 5, and I want the server to receive 3, 4, and 5 and send this packet up to my application. Again, TCP's point of view doesn't care what application it is, but if you try to cast back and think about how HTTP works, essentially what you're doing is, at this point, the GET request gets to the browser or the server looks at the GET request, figures out what to do, then it creates its own packet, which is the index or XML, for example. The exact same thing happens. The TCP on this side will break it into pieces and send them, and the expectation is it will get there in order, and then it will be sent up. But it need not be in order. So for example, let's say I'm trying to send 3, 4, and 5, and 3 gets here. This is a little bit hard to explain, but let me just, for now, just assume that I'm sending 3, and I get back an act for 3, and I get send 4, but 4 takes forever, right? Okay, I'm going to try, this is a little bit hard to explain before I'm explaining how reliability works, but let's go with this just for a second. Okay. Let's assume that I'm sending 3, 4, 5, and I'm receiving them on the other side. And I don't receive them in order, okay? What should I do? What should TCP do? Let's say I receive 3 and then I receive 5. What should TCP do? And then what? Wait for it to send more. While it's waiting, what will it do? Just store these 3 and 5 somewhere, maybe? Yeah.
Arrange the packets in order.
But then, okay, yes. What you're all saying is correct. I'm just looking for what's but that's all. Yeah.
Maybe add 5 to like the regular buffer.
That's exactly where I was going with. So what you do, you actually add a 5 in a temporary buffer and wait until you get 4 so that you can send them, right? So because, okay, you should remember that at this point, the TCP on the client's server side has nothing, right? It gets a packet, it sends it up. Gets a packet, it sends it up. Now it gets a packet. I can't send it up. Why? Because it's not in order. I need to wait. What am I going to do? I need to have a buffer that will store this information. Which means actually me, that is the server TCP, should have such a buffer, right? The resources are not free. So therefore you have a buffer. So, okay, so you need a buffer if you want in order delivery. You get a buffer. This buffer is called a receive buffer. It's called a receive buffer. And this receive buffer will store any packet that you get that cannot be sent immediately. So let's say that I receive 3 over here. 3 is in order, so I'm just going to send it up and remove 3 from the buffer. And then I get 5, so I'll store 5 here. I cannot send it up. I keep waiting. I'll wait until I receive 4. Somehow magically, let's say I receive 4. Then now I say, okay, now it's in order, so I'm going to send this up. And so the application would receive 3, 4, and 5 in order. Sometimes different implementations do something slightly differently. So some TCP versions won't send each packet up, it will wait for a bunch of packets to arrive and send it in. So for example, it could say, okay, I'm going to wait for 3, 4, 5 to come, then I'll send all of them together, rather than sending one by one. You can do these things because now you have a buffer, right? You can actually store this information. So that's how we that's how you do in-order delivery. So it's very easy. In-order delivery has you have something called a receive buffer at the receiver, and this buffer will essentially store any packets that were out of order, so that it's easy for me to then put them together. Will there be a receive buffer at the client side? Yes, because again, this is a two-way connection, which means that if I can get packets from the client to the server, I can certainly get packets from the server to the client. So I have to have a receive buffer on the client side. So both sides will have a receive buffer. In fact, both sides also have a send buffer, because sending can also take some. So you usually will have something called a send buffer here. And you have a send buffer because I would, for example, I get 3, 4, and 5. I may not be able to send this packet immediately after I get it from the application. I might have to wait just a little bit because maybe the network interface call is busy doing other things. And so that means that on both sides, when I create this TCP connection, I have to now have some resources available for both the send buffer and the receive buffer. This is something that happens when you do the three-way handshake. I told you that there's signaling. So as soon as the signaling gets over, what each of them will do is to tell their operating systems, hey, reserve this amount of space for my send buffer, reserve this amount of space for my receive buffer. Both sides will do that, and that's when we can start sending things. Because otherwise, let's assume that I don't have a receive buffer, okay? And I receive 3 and then I receive 5. What can I do? What's pretty much the only option? I just have to drop it. I don't have any other option, right? I just drop it. So instead you have this receive buffer. Alright, so that's how in-order delivery works. Fairly straightforward. Blah, 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 all these things. Now, the next thing you want to do is reliability. So this is in-order delivery. So you have a receive buffer on both sides. You have some size for these receive buffer. This is actually. So if you remember the TCP packet header I showed you last time, that actually has a slot called receive buffer. Okay, that tells you the size of this receive buffer. So I'll tell you in advance that, hey, this is the size I want to. This is the size of my receive buffer, and my operating system would reserve that much space for that connection. So this might actually sound like, oh, that's okay. How big can the receive buffer be? But remember that your computer has thousands of TCP connections at any given time, which means that actually that will add up. Which is also a reason why you want to close down this TCP connection, because if you don't, then the receive buffer is still there, and then you don't have space anymore.
Client and server communicate with each other what the receive buffer size is.
That's exactly, yes, correct. Both of them will let each other know this is the receive buffer size. Because this, okay, who decides what the receive buffer size will be? Okay, of which side? So, for example, let's say that the server in this case has some receive buffer size. Who decides that? The server's operating system, right? And the reason why this is important is this is actually what allows you to be able to communicate between devices that are of different sizes. A big server can communicate with an HPC, a high-performance computing device, can talk to your phones, can talk to a microcontroller, all over TCP. Why? Because each of them will say, hey, this is my receive buffer, don't send me more data than that, because that's my limit. Right? You can actually work with any of these receive buffer sizes, depending on whatever it is. So maybe a microcontroller doesn't have a lot of space, so they won't have a large receive buffer. I am a server, I can have a large receive buffer. So this is usually hard-coded, but yeah, you could change this number. Okay, so that's in order delivery. The second thing is reliability. Okay, polish. It's not that data does not get lost.
Does
Exactly. If it does, then I would know this, right? And I will do something accordingly. Because you cannot, well, okay, I'm saying you cannot, but the internet is built on this principle that you cannot expect the data not to be lost ever, right? You're never providing those guarantees. Because you know that if you have that kind of guarantees, the amount of resource you will need will make sure that you cannot scale it to the billions of nodes that we're scaling to. In fact, there is communication medium that provides you really, really large guarantees. Do you know what that is? Yeah. No, fiber optic cable is just a cable, right? It's not a communication medium. It cannot. You have to build something on top of it, and yeah.
So blockchain.
Oh, actually, blockchain provides you guarantees, but for storage, not for communication. But yes, blockchain provides you guarantees. This is a little bit old school. Telephone networks. I'm sure none of you have a telephone, actually not your phone. Your mobile phone provides you more guarantees. But this is your phone in your house. Like you might have some these phones that you take and dial. Those kinds of phones. They were big actually. They were as big as the internet right now. In fact, AT&T made all their money because of this. AT&T has a research lab where they said, oh, we make so much money, we don't know what to do with this. We're going to spend some money to do random research, which is actually why we are on here. But anyway, but the point is that they made a lot of money from this. Why? Because telephone networks were here to provide 5 guarantees, which is 99.99999. So the probability that there will be a failure is 0.501%, right? But that is very, very hard to do. If you have to do that, it will throw a lot of resources. It will be very expensive. It cannot really scale, which is I think very bold move from the internet, because internet was designed at this time when telephone networks were huge, and they still made this decision that, hey, actually I'm going to go completely opposite from what this existing communication medium is, and I'm going to say, I'm going to not provide it. So what all this be to say that reliability does not mean there will be no packet drops. That is impossible to do. Okay? All you can do with reliability is I'm going to try my best to mask your packet drops, and if I can mask it, sure. If not, I'm just going to say, hey, this connection is not bad. I won't be able to connect. Right? Those are the two options. So that's what TCP provides. It provides reliability. What is the easiest way to provide reliability? How do you provide reliability? Yeah.
If the packet gets lost, then you should ask the other side to get the packets again.
Right. So if the packet gets lost, you should just let them know and say, hey, send me this packet again. What is the way in which TCP does that? You already saw how it does. What's the mechanism used to make this work? Yeah. Sequence numbers only tells you what order it needs to be. What tells me that, oh, this packet is lost, or you need to resend this packet? Acknowledgement, right? So you use acknowledgements to say, acknowledge packets you have received, so that the other side, the sender, can perceive packets that have not been received. And that's how you do reliability. So, for example, you send a packet. The easiest way to do this is I send a packet, get a map. I send a packet, I get a map. And then if a packet is, okay, so every time I get a map, it means that the packet went through, I can go to the next packet. Right? This protocol is sometimes called stop and wait. And the reason it's called stop and wait is that you actually send it, you stop, you don't send any more packets, you wait until you get an acknowledgement. Once you get the acknowledgement, you move on to the next packet. So this is why it's called stop and wait. Okay, so you have the stop and wait protocol. If everything works fine, let's say I have 100 packets to send. This is fine. I send you a packet, get back an app, send you a packet, get back an app. I keep doing this 100 times. The last packet I send a packet, get back an app, I'm done. Everything is fine, it close. But what happens if I don't get it? What should I do at the sender side? I'm going to call the sender and receiver from now on, so it's just easy. It doesn't have to be right, both can send, both can receive. But I'm just calling one sender, one receiver, just What?
I'll wait for it a little bit.
Okay, so I wait for a little bit. I didn't get an app back. I'm going to perceive that, intuit that means the packet did not get there, and I'm going to resend this file, right? Okay, so let's look at that a little bit. I'm starting somewhere in the middle, okay? Not at the beginning. I send the packet, let's say 5. I got an add back, usually it will be for 6. This is the sender, this is the receiver, and I then send up this is the act equal to 6. This is the sequence number equal to 5. Then I send the sequence number is equal to 6. Okay, something happened. I did not get an act here. Okay, so the idea is I'll wait for a little bit of time and then reset this because I know that this packet did not go through. How long should I wait? Yeah.
Could it be like a function of the packet size that you wait?
Okay. Should it be a function of packet size? Okay, tell me why.
Because you can account for file transmission time as well.
Okay, you can account for the file transmission time. Remember, the act itself is not going to be bigger because the packet is big, right? But the packet could have taken time. Sure. Okay, fine. Anything else? Yeah. It should even more than the packet. Oh, actually, sorry. Wrong. It cannot be size of the packet. Okay, why? Because remember that the maximum of the packet is 1400 bytes. I cannot send a packet larger than 1400 bytes. 1400 bytes does not really take a transmission time, right? It doesn't matter whether I'm sending 1 byte or 1400 bytes. The amount of time difference is very, very small, so it doesn't matter. So, okay, so that's why packet size may not matter. What does matter is RTT, right? Okay, so let's say that I send this packet here, I send a sequence number, I get an add back. Roughly, what's that time? How much time does it take for me to send the sequence number and get an add back? 1 RTT, right? So this means that, like what you said, what's it? Okay, like what Sam said, if I have to wait, it has to be some function of the RTT, right? Because I'm expecting the act around RTT, so it has to be some function of the RTT. Now let's say that, yeah.
I'm sorry, but what happens if the act packets themselves are lost at the start of the connection? Because if that happens, then you cannot calculate the RDT.
Okay. What happens if the act gets lost? Let's discuss that in a bit. Okay. Let's go back to this original question. So you said I wanted to be the 90th percentile of RTT. Okay. So I think why you said 90th percentile of RTT was because I don't know what the RTT is. Every time it can be different. So I'm going to take all the RTTs I saw up until that time. Let's look at the 90th percentile. Okay. Let's put a pin on that for a second. Okay. Let's put a pin on how I'm estimating the RTT for a second. Let's assume I know what the RTT is. Random. Let's assume. Now, how long should I wait before I get an act, before I can send back this? Should I say wait 1 RTT? Roughly? No. Why not? It might take slightly longer, and I have decided that the act is not going to come back because at that exact RTT time, I didn't receive anything. I'm going to send the packet again. That's a waste of time. So I don't want to wait for 1 RTT exactly because it may go back. So how much should I wait? Yeah. 2. Okay, why 2?
Because the second time the client would want to send another package, so it would come back.
At this point, okay, I sort of get what you're saying, but at this point, think about what the client, the sender is doing. I sent sequence number 5, I got an act back, I sent sequence number 6. I waited an RTT, I did not get an act back. I'm not doing anything, I'm not sending anything at this point. Let me just stop and do it, right? So then I wait 2, why? Yeah.
Because it's like short, it's like a double check on a chance, and I
only one RTT, but I don't want it to be 5 RTTs either. I don't want to wait forever. Why? Because that's going to slow down my transmission. So I want to be something strictly greater than 1 RT, something strictly less than maybe 5 RT. Some number, I need some number. What's a good number? This is where actually, like, computer networking is a little bit more art and science, in the sense that I don't know. I'm going to try a few different things. Maybe I'll be creative and come up with some number and try if it works. Fine, I'm going to do it. Actually, the number they came up with is 2. Okay, so they said I'm going to wait for 2, but it's not really 2 RTTs. I'm going to get to that in a bit, because some estimation of the RTT. We don't know what that estimation is, but we want 2 times some rough estimation of the RTT. Now, because there's that question, how do I even know what the value of this RTT is? Because every time it's different. So that number, by the way, how long I wait before I transmit again, that is actually very important. You need to remember this name. It's called RTO. Okay, I will keep repeating this, but this is important to know. This is the terminology you need to know. RTO stands for retransmission timeout. As the name suggests, it's basically when I time out and I need to retransmit. So, for example, in this case, I said sequence number 6. I wait until this. I didn't get an act. I'm actually going to wait until what is known as an RTO. At this point, I say that the packet has been timed out. Okay? A timeout occurred, which means I can be pretty sure that sequence number 6 packet didn't actually go through. Therefore, I will send that out. Yeah.
Are you sending like the exact same packet?
Yes.
So if they receive it twice, it won't mess up anything?
Yes. Why? Because exactly why we don't want it to mess up anything, I'm going to send you the exact same. I'm not going to say anything different. If you get it, again, problem. Okay, so that's a very good question though. So why would you receive this twice? Because the act got lost. Can the act get lost? Of course it can get lost. Right? Am I going to do something about it? No, because this is best effort. I send it. I'm going to try my best not to send it too many times. But if I send it, you receive it again. Well, okay, so then I'm going to send the sequence number 6 again. And I keep going on. So now the question is, what should this RTO be, the retransmission timeout? This is called timeout. Like when okay, again, so you should know how TCP will work now, right? As soon as I send a packet, I start a timer, and if the timer goes off, I then reset the packet if I haven't received the app. If the timer, if I receive the app, I cancel the timer and send the next app. So there's some additional thing I need to do.
Previously, you showed us that the server has that buffer that has packets like delivered,
Yeah.
not an over, right?
Correct.
How did that happen if we delivered an over?
I was waiting for this question. Okay. Very good question. So, I said that before, I said, hey, if I send a packet, and I send 2 packets, and then the second one didn't go through, and it won't be on the buffer. But now I'm talking about the stop and wait protocol, then I only send 1 packet at a time. So how would it ever be out of order? It's a very good question. Let me first discuss how, this is the very first version. They didn't have out of order delivery at this point. After this, they had a slightly different version. That's where it's problem. Good option. Okay. So now we have this timeout. The question is, what should this RTO value be? It's actually the RTO value is calculated to be 2 times RTT estimation. So what is this RTT estimation? It's a rough estimate of what the RTT is. Again, Sam said, oh, it could be 90th percentile of all the RTTs I've seen so far. Sure, you can do that. You can again try different things. The way that we do this is you estimate this as a weighted average over the RTT value. So what I'll do, this is a very common technique that's used in networking, but also in other places. So if I have I'm observing some event and it happens over and over, and that event can be slightly changed every time. What you do is, if you want to estimate how long that event is going to take, what I will do is I will keep observing and then I'll do like an exponential moving average of those numbers. So, for example, first it was 0.9, then it was 1, and 1.1, and then 0.9 again, and so on. I take all these values, I will do some kind of like, it's not mean, it's basically an exponential moving average. That's the formula for it. And so essentially here 1 minus alpha times RTT plus alpha times new sample. That alpha is a number that tells me how much importance I'm going to give to the newest sample versus the historical sample. Alright, and usually people will give more importance to the new samples versus the historical sample. By the way, machine learning today solves the exact same problem, except slightly differently. Here this is just an empirical problem, that's it. Machine learning does the same thing, so have all these observations, what observation is. Yeah, it's sort of like that. But this is much simpler. And so this is how your RTT is estimated. So over time, you keep estimating this RTT, and at some point, then you use that RTT estimate, do 2 times of that, that's your RTT. And obviously, every time you send a packet and get back an answer, that number will change. The RTT estimation will change. Right? Okay. Alright. Okay, so now coming back to some of those questions, which is, hey, what happens when the very first act gets lost? What will the RTT be? Because I have no idea, right? How do I estimate RTT? I basically send them some request, I get back an act. That's how I know the RTT. Now the very first act, like the synapse, if that gets lost, the connection is not even established, so we don't have to worry about this. But let's say that the connection gets established and I use the very first act gets lost, then you still have that one number, right? You have that one RTT sample, you just use that sample. Will that be wrong? Yeah, sure, it will be wrong, but it's okay. Now, this is great, right? But at this point, actually, TCP works perfectly. Can do reliability, doesn't even need inorderability because I'm only sending one packet at a time. All fine. What is the problem? Yeah.
It's slow because you send one packet at a time.
It's very, very slow. You send one packet at a time. Your page is never going to load if you're going to have TCP that sends one packet. This is not relevant. What can you do instead? Yeah. Pipelining. Okay, tell me what that means.
So rather than stop and waiting, you send out multiple.
Correct.
Exactly.
Actually, it's pretty smart that you call it pipelining. People didn't realize that that's actually the same as pipelining we do in the application layer. But yes, it's essentially pipelining. We just don't call it pipelining at this layer for whatever reason. Alright, so you do that. So instead of sending one packet and waiting, what if I send a bunch of packets and then wait for the acts, and then I send a bunch of packets again, wait for the acts, and so on. That's exactly what TCP does. So this is called as a sliding window protocol. Okay? So the sliding window protocol works as follows. I have a sender and receiver, let's call it that for now. And again, I'm somewhere in the middle. I need to send packets 5. Let me say that I have to find packets 5, 6, 7, 8, 9, and so I have to send all of these packets, and I'm going to say instead of sending one packet and waiting for the app, I'm going to use a sliding window. So let's assume my sliding window has a sliding size of 3. So what this means is that the definition of a sliding window is 3 is that I can send up to 3 packets before acknowledgement. I need to in the stop and wait, I could only send 1 packet at a time. I can have 1 outstanding packet that does not receive acknowledgement. But in this case, I can send up to 3 packets. So what I will do is I will send 5, 6, and 7. Okay. Now let's assume that at this point I received an act for 5. Okay. But what will this act tell me? It says 6, right? I'm expecting 6. It received 5, 6. At this point, what is the number of unacknowledged packets? Number of unacknowledged packets. 2. Right? I sent 3 packets, all 3 were unacknowledged. One of them I received acknowledgement, so now I have 2. That is, cut my sliding window size 3. Which means I can have at most 3 unacknowledged packets there. So, as the name suggests, you slide the window. So, I slide my window from here to here, and I can send 3. Now, the sliding window works in such a way that instead of 5, we will receive the acknowledgement of 6 first, I'll still do the same thing. It doesn't matter to me which of those packets they receive. As long as I receive an acknowledgement for some packet that I sent in the previous sliding window, I can slide it.
The size of the sliding window is
Very good question. And yes, that's very good observation. We talk about that. They make a much bigger deal than what you just said, but yes, we do that. Yes. Okay, so yeah, that's how the sliding window works. So essentially, you can do. You keep waiting. Okay, so let's say that nothing happened, everything is perfect. There's no loss in the system. I sent 3 packets. What is roughly the time it takes for me to receive the acknowledgement for the 3 packets? Yeah,
3 RTTs.
3 RTTs, no. Just 1 RTT. I sent all of them at the same time. Right? That's the whole point of the pipeline. You just take 1 RTT. So instead of in 1 RTT sending 1 packet, now I'm sending 3 packets in 1 RTT. Okay? So that makes sense. So now it's faster. Obviously, sliding window on the internet is in the thousands. I'm just saying.